question. This is question 5, or at least a version of it. And it's essentially telling us to prove that this is a solution to that. So we've seen that type of question before. Prove that this is a solution to that. And we are going to do that. And so I'll take this fella here. Now, C is a constant, right? Just means it's a number that you don't know, right? It's a fixed number. You just don't have to know what it is. I need to find the derivative. So, would you agree that this is a quotient rule situation? Because it's a fraction. So I'm going to do f dash g, take away f of g dashed over g squared. Now, if you differentiate the entire top line, all you get is 2 over x, because plus 7 or plus c gets you 0. You then multiply it by g. You then leave the top guy alone, and you differentiate x, which is 1, and the whole thing is over g squared. And so I'm now going to take this guy and prove that it's equal to 2. So it's x squared times this derivative. Well, while I'm at it, why don't I go 2 times that and get you 2? Take away 2 log x, take away a c. So that's what that guy is. All over x squared. Plus xy. And that's going to be 2 log x plus c over x. Those 2 cancel and you're left with that guy. Those 2 cancel and you're left with that guy. And that gets killed off and that gets killed off, and just what you wanted. It's a perfect match. So we do have a solution. It does solve I'm going to have to do something with my dogs because they are scratching the heck out of our door, and that's not good. So if you hold off for a few moments, I will do that. Well, just like all bad parents, I've reinforced bad behaviour by giving both the dogs a treat to stop them from being annoying, which means that they have now reinforced that idea that if you make a nuisance of yourself, nice things happen. Now, my wife is down at the college today. She's in the office, otherwise she would have taken care of her. Now, before I forget, there is a second part to this question. This is a general solution to a differential equation, this differential equation. In the second part, they ask you to draw 3 or 4 versions of this. Now, what that basically means is that you go to your calculator, your TI-84, and you pick some numbers for C, and you sketch them all in one diagram. So I want you to imagine that I'm doing that, even though I'm not. So you do that version. Maybe I would do that version. Maybe I would do, say, that version. And basically, C is -1, C is 0, and C is 3, right? You pick any 3 you like, and you put them on your calculator, and you will get 3 different curves. And it might look like that, might look like that, and it might look like that. And then what you do is you've got a set of pictures to pick from, and you pick the one that looks like that. So, although I haven't done it, and that's not actually necessarily the right answer, that's how you're going to do it. Now, if I move on, we're going to have a look at, this is basically, I think, question 6 and 7. Here's the differential equation, dp by dt, and it's 1.7 p, 1 take away p over, say, 2000. I'll write that again, it's a bit messy. And we are being asked 3 questions. For what values of P is the population increasing? For what values of P is the population decreasing? And then the third one is, for what single value of P do we have what's called an equilibrium solution? Now, this is called a population model. Essentially, what we're saying is that the derivative, the rate of increase, so how many new rabbits you're going to have more next year than you've got this year, is given by 1.7, 1 minus p over 2000. So you might say, well, how can this answer the question, for what size populations will the population increase? Well, if you use the word increase along with derivatives, don't things increase when the derivative is positive? So we are looking for what values of p, by the way, there's a p there, what values of p make this positive? Well, can I start by making the assumption that p has to be greater than 0? Because if this is a population model, you must at least have some rabbits, right? You can't have none, because if you had no rabbits, you wouldn't be able to have any new rabbits either, right? Look at this piece here. Do you know for certain values of p, won't there be a positive number and the thing will be increasing? But for other values of p, won't it be less? For what values of p then will this be a positive answer and therefore the whole thing is increasing?
Less than 2000.
And that's the answer to what I'll call A. Now you want that in interval notation, I guess you would write it down like that, okay? So any number between 0 and 2000, the rabbit population will increase. So if right now there's 1200 rabbits, you can guarantee next year they're going to be more than 1200, right? It's going to increase in size. Now kind of the logic says the same thing here. When's it going to decrease? Well, it's going to decrease when this thing up here, right, is bigger than 2000. And in interval notation, 2000 to infinity. So if you've got 5,000 rabbits right now, next year the population is going to reduce. There's going to be fewer rabbits. Now you can imagine that might happen. If you imagine a contained environment, there's only so much food. If there's too many rabbits there, they'll starve to death, right? And you won't get as many. Now the third one is a term we've never used. What's called the equilibrium solution. We want to know what value of p, right, make the derivative, 0. In other words, the population has reached the number that it's not going to change. So next year, they're going to be exactly the same number of rabbits. Well, that means, 100 died and 100 babies get born, right? The total number is the same, right? What do you think that number's going to be?
2,000.
Correct. And there is a trivial one.
0.
Yeah. No rabbits today, there ain't going to be any rabbits tomorrow either, right? So that's basically, I think, question 6 and 7. Population models. These are quite good population models if you're interested in finding out more about them. They're called logistic models. They are heavily used in population prediction models, mostly to do with environments involving animals. So if you wanted to do it, you might do a model for the salmon population, right? You do a logistic model for it. What it does is quite interesting. If you sketch one of these, it looks like that. So if you start with 10 rabbits, the population will increase, but it will level off at 2,000. 2,000 is sometimes called the carrying capacity. So can you imagine it's a enclosed environment. There's only enough food for 2,000 rabbits. Nature, you ever noticed that if you leave things alone, nature will figure out its equilibrium point? How many tigers this forest can cope with, right? If there's too many tigers, they eat too many deers, the tigers starve to death. Fewer tigers, the deers get a chance, population of the deer goes up, right? Nature figures out, if you leave it alone, what it's got. If you do it with anything, this is a very predictable model. It does really good data. It tends to predict things really well. And it's used better than this model. Can you remember 141 models? Exponential models? Well, they're good for 3 or 4 or 5 years. In fact, if you sketch them together, they'll look like this. Do you see the problem with the exponential model is that roughly after 5 years, doesn't it get unrealistic? And in fact, if you use an exponential model and you use it to predict 100 years from now, don't you end up with Bremerton having the entire population of the world in it? Right. What the logistic model does, which is much more natural, is that it levels off at some equilibrium value, some carrying capacity is a term that they use. And let's get to quickly moving on here. And this one is going to be a visual one. And I'm going to have to rub out the solutions here. If you hang in here for a second. Will you all say hi while I'm doing this? I'll give you a chance to get your attendance. So let's get this show on the road. Make this a little bit bigger. What you've got here in question 8 is a differential equation. dy by dt is equal to this. And they've given you a curve for what the y, the original function is, right? Whatever it might be, y equals x cubed kind of function. And we're being told that this can't be a solution. And then they give you some sentences over here, and we'll fill them in a minute. But let me talk you through this. Would you agree that e to the t is always positive? And no matter what number y is, would you agree that y minus 1 squared is always positive? So my argument is that isn't this whole thing always positive? Shouldn't the solution graph, right, the real equation that's a solution to, shouldn't it be increasing all the time? What's the problem? Well, can you see that from here to here it's decreasing? That's the reason why that can't be the correct graph. So we're just going to fill in the data. The function is increasing and decreasing, but the derivatives tells us that it has to be greater than or equal to 0, implying that the graph has to be increasing. So it's like fill in the missing word or symbol. Now, this fella here also doesn't work. And you might think, well, what's the problem this time? Well, if you look at this piece here, when y is equal to 0, sorry, when y is equal to 1, won't the derivative be 0? And if a derivative is 0, shouldn't the graph be at least horizontal at that point? When you look at this graph at y equals 1, do you see it's not horizontal? That's why that shape can't be the correct graph either. Actually, if you look at this one, doesn't this one actually have a horizontal at y equals 1? But it had a problem that it wasn't increasing all the time. So each one had a problem with it, just a different problem. It's increasing, which is good, but it doesn't have a horizontal at y equals 1. So when y equals 1, this should be 0, but the thing doesn't have a horizontal tangent line, and that's what you would fill in. Now, in these graphs here, you are basically given 4 pictures and 4 differential equations, and you're trying to see which one of these guys, right, would match with which one of these. And you're typically going to be looking for things like what happens as x gets infinite, what happens to the derivative if x goes infinite, and sometimes when is the derivative going to be 0? Because if I know the derivative is 0, do you see at this one here, there's a horizontal tangent line, for example. So let's pick one. Question A. The derivative is equal to this horrible mess here. Now this derivative has to always be greater than or equal to 1. So you might say, well, how do I know that this must always be greater than or equal to 1? Well, think about it. Isn't x squared and y squared always positive? So the best you can get is 0 and everything else is bigger. Which wouldn't that mean the derivative is 1 plus 0 or 1 plus a number bigger than 0? So put that together, doesn't that mean I'm looking for a function that's always increasing? And because it's always increasing, won't that mean 1 and 2 are not the answer? Now, 3 is always increasing, technically so is 4, right? So now I'll bring in that what happens when x gets infinitely large? Well, if x gets really large, doesn't the slope, the derivative, get even bigger? So I'm looking for a function that's always increasing, but getting steeper as x gets further and further to the right. And put that picture together, and that's why I'm picking 3. So it's a bit like a detective. There's some clues here. You got to figure out which one of the 4 graphs match that. Now it's dead easy. Once 3's out the way, it can't be 3 again, right? So the next question, you only have 3 to pick from. And the last one's the easiest. Because if you got the first 3 right, whatever's left is the 4th one, even if you can't quite figure out why. There we go. So I am now going to move straight on. Without further ado, as they say in Old English, I think it's in Old English, Shakespeare anyway, without further ado, we are going to do 9-2. As soon as I get the darn thing picked. Gotcha. And a lot of 9.2 can be done really quickly. I'm going to show you the software that we're going to use a lot in this section. I think I picked the wrong one there. I didn't I? Right, let me try this again. Here we go. There's a guy called Geobra Slopefield. You click on this guy. There's a piece of software. It's better work. It worked good. That is basically going to generate what's called a slope or a gradient field. And you have a differential equation. It's here. And the one that I have here is question 2. Although you can't see it, I'm going to write it in. It says 2 take away y. Then click outside, and here is the direction field. And I'll take that guy out because we don't need him. And you will have 4 pictures, one of which will look something like that guy. And that's the guy that you're going to pick. So if you get questions like, here is a differential equation, here are 4 examples of what might be its slope field, you're going to pick the one that looks like that picture in front of you. I'm now going to go backwards a little bit and show you what a darn slope field is and why it's such a good idea that there's a piece of software that does it for us. So I'm going to pick as my slope field y dashed equals x plus y. Now, essentially what a slope field or a gradient field does is it tries to give you a visual representation of what this differential equation is saying. So you pick key places on your grid. So I'm only going to pick the whole number, guys. So can you imagine all these dots here? Every single one of them corresponds to one particular xy. And now I thought about it, I should have made this smaller, but it's too late now. Now, another way of writing this would be to say that dy by dx is x add y. Right. Let's pick one at random. You see this point here whose coordinates are 2, 3? Right, this one here. Well, at 2, 3, dy by dx should be 2 add 3, which is 5. So,
You mean 2, 1?
did you all catch that deliberate mistake? Right, so you got a slope of 3. I'm trying to find a green pen here. Oh, good, here's one. And at 2, 1, can you imagine I'm drawing a line whose slope is 5? Can you pretend that slope is 5? A little rise over run. You're saying something, Kathy? Oh, 3. Can you pretend that's a slope of 3? Right, got 5 in my brain today. Right, I'll try and pick another one. Let's pick an interesting one. Let's choose this one. At 1, -1, the derivative will be 0, which means at this point here, it would have a 0 slope. And can you imagine that you did this? And what you would end up with, and I'm making this up now. Tons and tons of these little guys. And that's a slope field. Now, a couple of problems. First is, they take forever and a day if you're doing them by hand. Would you agree you do not want to do this by hand? Right. Secondly, is that really a slope of 3, or is it a 4, or is it a 2, or is it a 5? Nobody can really tell by looking at it. Agreed? So you don't expect these pictures to be detailed, right? You don't be able to go and say, oh yeah, I can look at that and tell the slope is 3.5, right? You're not meant to use it that way. You're meant to use it in a kind of big picture way, because what it's essentially giving you is what this differential equation looks like if you try to visualize it in 2D. Now I'm going to continue with my pretend I know what I'm doing thing. There. Now, a second thing that you can do with a slope field, which thankfully the software will also do for you, is that sometimes you're given a differential equation, you've created this, and then they tell you, oh, we know the point 2, 1 is a boundary condition, right? It's for the solution it passes through it. So what you can do is you can use that guy, and you can say, okay, what does that mean? It means, well, it goes up that way. Now, this one comes down that way, it hits this one, then it comes here, and then it hits this one, and it comes here, and it hits this one, and it goes there, and then it goes like that. Can you imagine that you can draw a pathway, a very crude pathway, but wouldn't that represent probably one of the particular solutions? And if you chose a different point, can you imagine you get a different curve? And each one of these would be one particular solution to that differential equation. So now I'm going to return back to that piece of software that we showed you. And I hope that you'll appreciate it a little bit more. Isn't that a nice slope field for that particular one? And I'm going to click on what they call solution 1. Now, this one is pretending that you were told that 2, -1 was a boundary condition, right? A point that you knew. The cool thing is that you can pick this up. And do you notice that that has changed quite different? You see that? And let's put a third one in. Let's put a fourth one in. These are 4 different possible solutions to that differential equation, right? 4 particular solutions to it. And they do have some commonality about them. Do you notice that they all end up leveling off going this way? And isn't that at y equals 2? And what's special about y equals 2 is the derivative is 0. So can you imagine once the curve hits a y equal 2, won't it flatline horizontally for the rest of its life? That's called an equilibrium solution. So if you want to visualize what does it look like, if I take all the graphs away, because it's kind of less obvious, can you see it now? So far, so good. Now, I want you to keep that kind of photographic memory, which I don't have, although I have a visual memory, it's not photographic. And I'm going to go and we're going to look at the homework, and we're going to see what we're being asked to do. If you look at these 4 pictures, top left, top right, bottom left, bottom right, which one of those 4 was the guy that I had?
Bottom left.
Okay. That one? Right. Now, do you see how quick your homework's going to be? When you go to that piece of software, put in the differential equation, look at the 4, look at the picture, look at the 4, pick the one that looks the same. Now, it's not going to look exactly the same. Can you see that picture has a lot more lines in me? So think pattern, not, oh, it's a perfect match. It's got the right shape, right, the right pattern to it. Because couldn't you make the X's and Y's different scales, and that would make it fatter or taller, and therefore it would look a little bit different because of that. Okay, this one is X 4 minus Y. So X in brackets 4 take away Y. Can you see any equilibrium solutions in question 3?
4.
Right, Y equals 4. So shouldn't we get a horizontal line at Y equals 4? Agreed? Looking at those 4 pictures, is there only one of them that has the horizontal line at Y equals 4? Can you see a horizontal line at Y equals 4?
There's 2 that have that.
Oh, where's the other one? Oh, there is. Darn it. Doesn't that mean I'm going to have to use my graph then? But at least I know it's one of 2. So I'm going to have to do this pop out and pop in again, and hope you don't get dizzy. Right, click out. Okay, that's what it looks like. I think I can I zoom in and zoom out in this thing? Yeah, well, it doesn't really help much because it doesn't do any more of the pictures, but
Maybe if you change the Y min and Y max.
yeah, that should do it. You would think. Let's play about with this. I probably should change all of them as well, right? Including the X's. Okay, and yeah, I guess it just separates them more so you don't get too much advantage. But there is enough there, I think, for us to make up our mind. I'm saying that and then I'm not convinced anymore. Did I type that in right? 4 minus Y. Okay, keep that picture in your brain. And we'll return to this fella. I know it has to be either the second one that's top right or bottom left. Which one of those 2 is this guy?
Bottom left.
Couldn't you look at
Yeah,
it
bottom
and determine that there's no symmetry and then it's top right?
Okay,
Because
so we
there's
got
no
top right.
way.
Right, I've just thought of something else to do. And I'm not saying that's not a bad idea because I think what you said is a good idea. And I just realized that doesn't the bottom, aren't the range -2 to 2 here? So I'm going to return back to my picture. And see if that helps. And the one that I've got ends up being that guy. So that's the one that works. Okay, next fella. Oh, and they go give reasons, so that's something different. Let's just talk through it. Can you imagine I plugged that one in and we could look at the pictures? Can you imagine I plugged this one in and look at the pictures? Okay, there's something a little bit more interesting. 5/2y. So although you can't see me doing it right now, I'm typing that in. I'm just going to call it 2.5 because it's easier to type. And it's going from what, -0.6 to, so I'm changing the window to be -0.6s. And hopefully that'll match up better with one of the 4 pictures that we have here. And I'll click out. And some's not quite. Okay, I've screwed up. Okay. You can't see what I can see, but basically I hit something I probably shouldn't have hit. Move things too much. I'm seeing if I can fix it now. Right, I think I've managed to fix it. Okay, we're good. You'll have fun playing about with the little guys at the top, at least. That's one way of describing it. Click on that, go away. Right, that's basically what the thing looks like, right? And now we are going to put in some choices. Hey, come in. Oh, darn it in space. That was a really weird way of doing things, but at least I got it. There. I finally got a point and I put it on the curve and I drew it. Now, if I take this point and I move it up here, I get this guy. If I choose this one, I get this guy. When you look at all the choices that you've got, let me return now to the homework. The one that works is that one. So y minus 3x is the next guy. So the derivative is y take away 3x. And the window is going to be negative 3 to 3. So I'm just setting this fella up. Actually, I should probably show you me setting it up, because this is the kind of thing you wouldn't want to do. So I already typed in the thing. I'm choosing the windows sizes that they add, 3. Now I'm going to go and zoom out and zoom in. There. I can keep my finger on the mouse and I can shift it a little bit. There we go. So you get a gist of the particular gradient field. Now, they tell us in this question that 1, 0 darn it. How do you stop it being that? Do you go here? There we go. Try to find 1, 0 as darn close to as I can. There we go. Now, do you see at 1, 0, that's the sad face green curve? Can you trust me that that's picture 3? And we're good to go. So I'm going to keep that on and just tell you the picture. Right, so in the next question, which is question 8, we're going to do a 5y add 25 xy.
You
And the
have a Y
windows,
in front of that 5Y.
Why did that get there?
And if you increase the density, it makes
Uh-huh.
the graph look more like the ones
The
on the
thing they've
homework.
got. Good advice. So I got this guy in. It's negative 0.66, so I'm changing the window to suit the range in X and Y that they have. And the Y values go 3 to negative 3, that's good. If I make the density, oops, come on, increase, and then I'm just using this to, there. It's pretty close to what we want, right? Now, in this question, 0, 1 is our key guy. So can I get a 0, 1? Okay, I got this guy. I just need somebody I can pick up and drag somewhere. Oh, I need the point there. So if I do 0, 1, it's there. So I want a happy face in this guy. And the happy face is kind of over in this quadrant mostly. And that would be my case picture 4, bottom right. Okay, you'll probably get much better than I am at this, but can you imagine I stick in a second one here and a third one here and the fourth one here, right? If you take this guy, I probably can change it to red. Oh, it's just a dot. No. Can I do anything else? Well, you can play about with it and do other things. So what's the last thing we've got to do? Now, a little bit messy. Don't think it's that hard. Hopefully it's not, but it is a little bit messy. You're not given an equation, so you can't use the software. What you are given is a pre-made gradient field and a point. Now, the way you interpret that is when X is 0, Y is nothing 0.5. So can you imagine me plotting the point 0, nothing 0.5, which is roughly about here. Now, me visually, I think of this as like a water current, right? A weird kind of water. And I've just dropped a little paper boat at 0, nothing 0.5. And now I'm going to see where that little boat would travel. Well, as you move this way, do you see it would curve up and then go like that? And if you move this way, won't it go up and look like that? So don't I want a kind of curved U shape? And I'm pretty sure it fits that one, right? Now, the next one is 0, 2, right? When X is 0, the Y coordinate is 2. So if I go to 0, 2, I'm up here. And if I'm here, don't I get a little curved kind of U shape as well? But quite high up. Did I do that? 0, 2? Oh, there you are. It's that one. Can you imagine doing the same kind of thing with the others? That you take the gradient field. So here's another example. So 0, 2 would be here. If you're at 0, 2, can you imagine on this shape it kind of curves up the way, and in this shape it goes quite straight. So it would be a happy face, straight line, kind of curved up. Happy face, straight lined, curved up. Oh, check the point. Has to be that one, right? Because it started there. The answer's dead easy. You put a dot, right? You don't write much. You don't do any math. You just got to visualize it. If you find it hard to visualize, print that damn thing out and then just draw on it with your hand, right? With some pen, and you can see it there. And more of the same. And Mick Jagger, and more of the same.